Hello and welcome to my video lesson 1.5 on energy and momentum conservation. Momentum is conserved in collisions while kinetic energy is not. Okay, that's the big idea here. Kinetic energy and potential energy can be directly transferred only when discussing one object, but right when there's a collision, we now have to talk about momentum. So when there's more than one mass, masses being added together, being broken apart, whatever, you need to be talking about momentum. Okay, perfectly elastic collisions do 100% conserve kinetic energy before and after. The truth is that 100% conservation of kinetic energy doesn't really happen. That only happens with like subatomic particles and such. So it doesn't really happen in real life, but we can get close to it in certain example questions. So we will sometimes assume an elastic collision. So here are different types of elastic collisions. You can have a stop and go situation where whatever comes in knocks into something else and that other thing goes. So let's just kind of draw this out. So if you have a ball, it comes in and knocks into a different ball, the other ball goes flying, but now the blue ball stays there and stops moving. Actually, better yet, it'll stay here. It'll stop moving at that moment. So right when it knocks into it, the red one keeps going and that's it. So Newton's cradle is a good example of this. The balls kind of hit into each other and knock the other one out, but the first ball stops moving. Both in and out is another type of elastic collision. So the belly bump, if you've ever done that with a friend, where you, or maybe seen it in the movies, when two people jump up in the air and they knock into each other and then they fly backwards afterwards. So they're both flying in opposite directions after they do the belly bump. So that is both in and then both out, rebounding with opposite vectors. That's the big idea here. Whereas the first one was full energy transfer from one object to the other. This one is now opposite vectors. Okay, and then the third one is 1 in, 2 out. So pool balls that are moving at different angles. Oftentimes you'll have one come in at one angle, one come in at the other angle, and then they will bounce out at different angles at the end. And we showed this in class, and you can envision this pretty well as you can look at the last topic, and we had an example question like this in that topic, 1.4. Fully inelastic collisions, so the opposite of elastic must be inelastic. So inelastic collisions do not conserve kinetic energy and will collide and stick together. So if it is a fully inelastic situation, they will stick together. That's the big idea. Is anything fully inelastic? Yes, they're hard to find, like hard to have exactly perfectly inelastic. Usually there's a tiny bit of rebounding that happens, but again, we can get pretty close. Okay, so let's take a look down here at two different examples. Okay, example 1 is an outfielder catching a fly ball in his baseball glove. The ball was traveling at 35 meters per second when it hits the glove. If the glove was that heavy before the collision, how fast is the glove and ball moving immediately after the collision? So the big idea here is, well, this is the glove and ball moving at the end. Okay, so because it's the glove and ball moving at the end, when we write our momentum statement, it's the total, whereas at the beginning we have the ball and we have the glove. And really at the beginning it's just the ball because the glove is not moving. So it's the momentum of the ball initial equals the total momentum at the end. So MBVI equals MTVF. MT is just a stand-in for the mass of both together, or total mass. So if we're finding the speed after the collision, then we're going to have to subtract by mt on both sides. So we're going to have mBVI over mt equals Vf, or another way to write that is mBVI over m plus mb, not multiplying. Okay, and now we can plug this in our calculator. So we should have 0.145 times by 35 over 0.145 plus 0.6121, sorry. And then we get a speed of 6.625 meters per second. And this is immediately after the collision, just before the person starts to react and start to slow down the ball. Okay, so the question is now asking, is the situation elastic or inelastic? So how can we tell? Well, what we can do is look at the initial momentum values, or these two values, and we can look at the final momentum, or the final mass and velocity, whatever is moving, and we can compare them, but using kinetic energy now. So kinetic energy initial is mBVI squared over 2, because it's mv squared over 2. And then same sort of thing for the kinetic energy final. It's mTVF squared over 2. So let's plug that in. So we have 0.145 times by 35 squared over 2. And we get 88.8125 joules. Let's just keep in mind we've got sig dig, so 89 joules. Okay, and let's try the other one, which is 0.145 plus 0.621, yes, bracket times by our new speed, which is 6.625 squared over 2. And good, it worked out. I was a little bit worried there for a second. I'm always worried when I make a new question. 17 joules of energy. So you can see here that it's nice and clear that our energy has decreased significantly. If there's only a tiny bit of energy loss, we can usually say it's basically elastic. But if there's a lot of kinetic energy loss, then it is inelastic. And considering the fact that the person's glove is actually catching the ball, and now the masses are counted together, that is your big hint that it's going to be inelastic. So this here tells you that it's going to be inelastic. This is the big hint that it's MT, right? Or if you can see that the energy decrease, that's also, I mean, that's the definitive proof that it's inelastic. All right, let's scroll down and take a look at one more question here. Okay, so anyways, we've got a ballistic pendulum of mass 2 kilograms. We're catching a bullet that weighs 23 grams. Determine the bullet's initial velocity using the height it reaches when it's at a maximum of 25 centimeters. Pause the video now, try it yourself, see if you can get it, and then press play. So essentially here, what's happening is that we can use the idea of potential energy. So at the end of the situation, it has potential energy. This is mgh. Now this m here is mtgh. It's the total, it's the mass of the pendulum and the bullet. It's both. Okay, and then you can go backwards to the moment that the pendulum starts to move. So the moment it starts to move, that's our EK. And I'll call it EKI. Okay? So now we have mt v squared over 2. Now, the kinetic energy is being completely transferred to potential energy because it's at the maximum. That's why that word, it wasn't super clear before, but that word is super important. So we're going to then have mt v squared over 2 equals mt gh. And now that you have that, you can actually see that the MTs are going to cancel, and we're solving for the V. Now the V squared is not going to be our final answer, by the way. We'll talk about that in a second. Or the V is not going to be the final answer. So this is the velocity of the pendulum with the mass total, right? This is the mass total, right? So it's the mass, or the velocity of the pendulum together. That is what we're finding right now. So that's using energy to get there. But let's consider this as VF. Why VF? Because now we can talk about this as our VI. So now we can talk about these 2 situations where we have your momentum total final, and you have your momentum bullet initial. And those 2 things have to be equal. So first you do the purple part, now you can do the red part. So now we're going to use m bullet B, vi, that's the bullet's initial velocity, equals mt, this is the total for the bullet and pendulum moving, vf. This is the vf that we just quote-unquote calculated. We haven't actually gotten a number here, but that's the right idea. So now we're going to look for the bullet's initial velocity, which is this vi. So now we have mt vf over mb. Or we could write this again as mb plus m pendulum, I'll just call it a, vf over mb. So let's go ahead and calculate this and see what we get as our final answer. Actually we can't continue yet. Let's take the VF and put in the thing that we solved for, the whole square root 2GH. That's what we need to put in for the VF. So my bad. So let's put that in. So square root 2 times 9.81 times height, which is 0.25, over MB, which was 0.023. There you go. And yeah, it looks like we're a little slow for a real life bullet. So maybe this is an air gun or something. This seems a little bit slow, but that's okay. I tried to keep the numbers realistic-ish. It's not perfect. 2 sig digs though, so it should be 1.9 times 10 to the 3 meters per second. Alright, so I hope that this video helped you better understand the difference between conservation of energy and conservation of momentum, and how to use both together, especially with elastic and inelastic collisions. Hope the video helped, and good luck.